In this lesson, we will focus on the comprehensive process planning and case studies of typical parts in Project 3, specifically emphasizing the development of process rules for milling, planning, and grinding in Task 3.1. We will delve into the characteristics and application scenarios of the three machining processes: milling, planning, and grinding. You will learn how to develop a reasonable process route based on the specific requirements of the parts. Additionally, we will use real-life case studies to deepen your understanding and application of this knowledge. Overview of milling, planning, and grinding processes. A. Milling process. Milling is a cutting process that uses a rotating milling cutter to machine various surfaces on a workpiece. The milling cutter is a multi-edge tool, with each tool functioning like a lathe tool fixed on the rotational surface of the milling cutter. The scope of milling is extensive, capable of machining flat surfaces, stepped surfaces, grooves, and contoured surfaces, among others. For example, in mechanical manufacturing, the milling process is often used for machining flat surfaces of many parts, such as the bed and housing of machine tools. The characteristics of milling include high production efficiency, as the multi-edge tool cuts simultaneously and can use a large cutting volume. The machining accuracy is moderate, generally reaching IT7 to IT9 levels, with a surface roughness raw value of 1.6 to 6.3 micrometers. There is an impact during the milling process due to the entry and exit of the cutter teeth, which causes variations in the cutting force. B. Planing process. Planing is a cutting process that uses a planer tool to perform horizontal relative linear reciprocating motion on a workpiece. Planing is primarily used for machining flat surfaces, horizontal, vertical, and inclined surfaces, and grooves, straight grooves, T-slots, dovetail grooves, etc. For instance, in the manufacturing of some simple molds, planing can be used to machine the parting surfaces of the molds. The characteristics of planing include: the tool is simple, making it easy to manufacture, sharpen, and install. The machining accuracy is relatively low, generally at IT9 to IT10 levels, with a surface roughness raw value of 3.2 to 12.5 micrometers. And the production efficiency is low because planing is a single-edge cutting process, and the return stroke does not involve cutting, resulting in idle stroke losses. Grinding process. Grinding is a method of machining the surface of a workpiece using abrasive tools, such as grinding wheels and abrasive belts. It can process materials of various hardness levels, including hardened steel and hard alloys. Grinding is often used for the finishing of parts, such as the external cylindrical grinding of shaft parts and the internal cylindrical grinding of hull parts. The characteristics of grinding include high machining accuracy, generally reaching IT6 to IT7 levels, with a surface roughness RA value of 0.2 to 1.6 micrometers. It can process materials with very high hardness. The cutting speed during grinding is high, generating a significant amount of heat, which requires a large amount of cutting fluid for cooling. Basic principles for developing process routes. Datum first. When machining parts, the datum surface should be processed first. The datum surface serves as the positioning foundation for subsequent machining, and its accuracy directly affects the machining accuracy of other surfaces. For example, when machining shaft parts, the center holes at both ends are usually processed first, using the center holes as the positioning datum to machine the external cylindrical surface. B. Roughing. Before finishing, begin with rough machining to remove the majority of the machining allowance, followed by semi-finishing and finishing to gradually improve the machining accuracy and surface quality of the part. This approach is necessary because rough machining involves large cutting forces and generates significant heat, which can affect the accuracy of the part if finishing is done directly. For instance, when machining a flat surface, rough milling is first used to remove most of the allowance, and then finish milling is performed to achieve the required accuracy and the surface roughness. C. Primary. Before secondary machine, the primary surfaces first, followed by the secondary surfaces. Primary surfaces refer to the working surfaces and assembly surfaces of a part which require higher accuracy and surface quality. Secondary surfaces, such as keyways and threaded holes, are generally machined after the primary surfaces. D. Surfaces before holes for parts such as housings and brackets. It is generally preferred to machine the flat surfaces first, and then use these surfaces as a datum to machine the holes. This is because the large area of the flat surface provides stable positioning, ensuring the positional accuracy of the holes when they are machined using the surface as a reference. Steps for developing milling, planing, and grinding process route C. Part analysis first. Conduct a comprehensive analysis of the part, including its structural shape, dimensional accuracy, surface roughness requirements, and material properties. For example, for a part with a complex shape, it is necessary to consider which machining method can better ensure its shape accuracy. For surfaces with high accuracy requirements, an appropriate finishing process must be selected. B. Selection of machining method. Choose the appropriate machining method based on the part's machining requirements and material characteristics. For instance, if the flatness accuracy requirement of the part is not high and the production volume is small, planing can be selected. If higher accuracy is required, milling or grinding may be more suitable. For some complex-shaped grooves, milling might be necessary. C. Division of machining stages. Following the principle of roughing before finishing, divide the machining process into rough machining, semi-finishing, and finishing stages. In the rough machining stage, the primary goal is to remove the majority of the material allowance. The semi-finishing stage prepares for finishing by further improving accuracy and reducing surface roughness. The finishing stage achieves the final accuracy and surface quality requirements of the part. D. Determination of process sequence. Determine the sequence of operations based on the principles of datum first, primary before secondary, and surfaces before holes. For example, for a part with holes and flat surfaces, machine the flat surface first as a datum, and then proceed to machine the holes. Additionally, consider the connection and coordination between each operation to avoid the accumulation of machining errors. Case study analysis. Let's assume we need to machine a rectangular part made of 45 steel. The top surface and sides of the part have accuracy requirements, with a surface roughness raw value of 1.6 micrometers, and there is a T-slot. A. Development of process route 1. Rough plane all 6 surfaces to remove the majority of the material allowance and ensure the basic dimensions of each surface. 2. Finish mill the top surface and sides to meet certain accuracy and surface quality requirements. 3. Mill the T-slot using a specialized T-slot milling cutter. Milling 4. Grind the top surface and sides to further improve accuracy and reduce surface roughness, achieving the final machining requirements. B. Integration of ideological and political elements. In this case, when developing the process route, we must adhere to internationally accepted machining standards and norms to ensure that the quality and the performance of the part meet international requirements. Additionally, throughout the machining process, it is essential for each operation to coordinate and cooperate effectively. From rough machining to finishing, every stage must be optimized to create a high-value part. This reflects the ideological and the political concept of planning according to international standards and collaborating to create optimal value. V. Considerations for developing process route C. Consideration of production volume. The size of the production volume affects the development of the process route. For large-scale production, efficient specialized equipment and processes are typically used to enhance production efficiency and reduce costs. For small-scale production, greater emphasis is placed on the flexibility and versatility of the process. B. Selection of equipment and tools. Select appropriate equipment and tools based on the machining process and part requirements. For instance, milling surfaces of different shapes requires different types of milling cutters, and grinding materials of varying hardness necessitates choosing grinding wheels with different grit sizes and hardness levels. C. Determination of machining allowance. The size of the machining allowance directly affects the machining quality and production efficiency. An excessive allowance will increase machining time and cost, while an insufficient allowance may not ensure machining accuracy. When determining the machining allowance, factors such as dimensional accuracy, shape errors, and deformation from heat treatment must be considered. In this lesson, we focused on the comprehensive process planning and a case study of milling, planing, and grinding for typical parts in Project 3. We specifically studied Task 3.1, which involves the development of process routes for milling, planing, and grinding. We have learned about the characteristics and the application scenarios of the three processes: milling, planing, and grinding. We have mastered the basic principles of process route development, including datum first, roughing before finishing, primary before secondary, and surfaces before holes. Through practical case studies, we have learned how to develop a reasonable process route based on the specific requirements of the part. We also recognize the importance of adhering to international standards in process planning and coordinating each operation to create optimal value. Additionally, we understand the need to consider production volume, equipment and tool selection, and machining allowance when developing process routes. I hope everyone can further consolidate this knowledge after class and enhance their process planning skills.